Good afternoon. My name is Mark Hoerber. I'm a recent graduate from Florida Atlantic University, as stated. I just obtained my degree in Bachelor's of Science in Mechanical Engineering. I also spent 8 years in the Marine Corps, and so just a little bit about me. It's one of the things that have been able to motivate me to be able to get this. So what I did in partnership with one of Sean's friends, his name is Rolando Brandley. He's out of Broward College. He's part of the inspiration for this project. He came to me with a problem and said, we want to build a device to perform a biological experiment in space, and can you help me? So this is what I kind of came up with. So the problem is, we've noticed that through the prolonged space exposure, astronauts' immune systems are weakening. Via this, we also can find out that viruses and bacteria tend to replicate and become stronger. So what does this mean for us? How can that benefit us? What we want to do is be able to grow these things and be able to study the RNA components of their DNA. So the proposed solution was utilizing the CubeSat Launch Initiative program to utilize their size constraints to be able to do this. Sorry, I'm just a little nervous. I'm skipping through real fast. So the main purpose of this is we want to know if we can grow bacteria or viruses in space. Well, we utilize viruses to help combat current illnesses. So if we can make viruses stronger to combat illnesses, we may have a better shot to beat autoimmune, HIV, and some cancers, hopefully. So some of the design constraints that I was given is I was given a 1.5 unit, a 10 centimeter by 10 centimeter by 15 centimeters, a weight constraint of 1.5 kilograms or 3.3 pounds. The apparatus I was told to grow 3 individual bacterial experiments. And also they wanted to know what the temperature is inside. All this will need to be performed in a biological environment. Therefore, when you're growing bacteria in a petri dish, you have to relocate it after a certain amount of time because it starts to live in its excrement. So we also needed to develop a system to be able to do that. So some of the considerations for the design here is we need to make sure that the apparatus is durable. And we had to make our own petri dishes because through research, maybe they were out there, maybe didn't look at enough places, but we ended up making some of our own. We needed to have this, as other people said, autonomous. So we've incorporated a microcontroller to perform all the actions that we needed to do. So what we did is we found that utilizing some 6061 aluminum, which you'll see in some later slides, that is what we're going to mount all our hardware to. We're going to separate these, what we call plate stacks, via polycarbonate rods, and have the apparatus enclosed with a polycarbonate sheeting. The reason why we were thinking about utilizing polycarbonate and having it sort of loose fitting, as if any of you have seen it out there, is the extreme vibrations on the launch up. We can go and over-engineer, make things really durable, but if we can utilize some soft material where we can disseminate that vibration energy into the apparatus without actually transferring it through or needing just to deal with it, we thought that would be a good idea. We chose to make our petri dishes out of ultra-high molecular weight polyethylene due to its durability as well and its resistance to cracking low temperatures, which will be expressed in a little bit. We chose to use an Arduino Demalia microcontroller because it has enough computing power, enough IOs, in addition to being able to fit within our size constraint. How are we going to perform the relocations? Well, we introduced 2 sets of separate controllers. One set of separate controllers, separate motors, will perform scooping action to initially deposit and collect the samples for while needing to relocate it, whereas the other one will be rotating the dish to allow it to go into its appropriate spot. And one thing that some people are also saying, modular. Things that are modular tend to be a lot better because what if somebody wants to say, well, I don't want 3 dishes, I want 9 dishes. Well, I want to increase it to max size of a 3. Well, then if you design something for one constraint, well, now you got to go redesign essentially. Whereas this design can be either shrunken down or expanded to whatever you see fit. So some of the fabrication that we're doing, I utilized a CNC mill to cut, that's the polycarbonate, right, the ultra-high molecular weight polyethylene here, and these are the petri dishes being cut out. After this, because it is a student or a school mill, it has some play into things. It wasn't exactly perfect. So I took the dishes and I turned them on a lathe to get them perfectly round. Here's a picture of the Arduino and a micro SD shield that we are going to incorporate on top of that. We felt that even though we are working with nanoracks, that if we had our own data logging capability, that would also prove useful. In addition, that little surface mount area here allowed us to attach our capacitors in a wire hookup for the stepper motors themselves. Utilizing a new water jet that my school acquired, I used this to cut the 6061 aluminum into the shapes that you can see here. Here's a picture of it being displayed at my senior design presentation with this brief electrical diagram here, and this is from my school as well. So in conclusion, citizen scientists should be able to apply this apparatus to be able to find other useful things, hopefully. The device was built on the concept of open source due to the fact that most of the programming was open source and modified to control the device. We intend to open up the research because we want to make the space industry usable. Again, focusing on open source. We don't want to keep the knowledge just to ourselves. We want to make it, you over here and you over here have access to it, because the more people involved, the more design changes that can be submitted and we can make things better. So again, we want to thank NanoRacks, Silicon Valley Space Center, and NASA, because they are going to help us get our project up to the International Space Station later in this year or the beginning of next year. We are trying to work with the Kickstarter campaign to help also, not this as our initial prototype, but the second phase for the bioreactor, to be able to get it so if schools want to be able to copy this or be able to do it, we'll be able to have some sort of parts ready for them as well. So if anybody else feel that they have useful knowledge or ways of supporting, later on I will be having an conference on this, and anything that you have to submit idea-wise to me to help me improve it, I welcome that, as well as any other questions I can answer at that time, I will do so. So this project constitutes one of the first fully instances of a truly commercialized space product that can be built and used up there and then be able to turn around and no problem. So at this time, I would have opened up for questions, but we're going to save that for later. I thank you for your time.